Okay, so I was tasked to discuss the circulation of atmospheres, actually generally, and so that's a bit of a broad topic. So I thought I would make it worse and add volatile cycles in there. Um, if you read my abstract, you'll see that I mentioned Mars and Pluto and all this, but I actually am going to cut out volatile and just put in hydrologic and talk about two bodies in the solar system. I'll let you know which ones a little later. You could probably guess. Okay, so I'll get started here. As we've heard a number of times in this conference already, the solar system alone presents a beautiful range of bodies with atmospheres, with which we can begin to study the diversity of climates, independent of exoplanets. So I've put up 4 of them here. Obviously, these are all terrestrial bodies. The giant planets add to this diversity, but I won't really discuss them here. So we have Earth, Mars, Titan, and Venus. And you can see I put on the bottom the range of the rotation periods and atmospheric masses in terms of the surface pressure. For these planets, you can see that both of these parameters, which are really important for climate and the atmospheric circulation, span 3 or 4 orders of magnitude. Actually, almost 5 orders of magnitude in the case of mass. And so, with this alone, we have a huge range of options and the ability to study the diversity of planets with the diversity of climates with planets which we can really resolve and of which we have very good data. So this is great. You can probably imagine that I'm going to focus quite a bit, in fact, on rotation. Just based on what I've put up here. We've already heard about this, and there's a number of people here who have presented work looking at the impact of rotation on different aspects of climates. So hopefully this is not too much of a review for folks. Okay, I've split this talk into 2 bits. One is on specifically the circulation, sort of an overview of circulation basics, and then I'll talk about the hydrologic cycle and its interaction with the circulation a little bit at the end. Okay, so begin with the first part. So as I said already, the planetary rotation impacts the atmospheric circulation of different planets in a very important way. So fluid dynamics in general are strongly affected by rotation, and this allows us to do things like use water as a really beautiful analog for atmospheric dynamics. So this is just an example from an outreach event that I've been working on, an outreach program that I've been working on called DIY-namics, Do-It-Yourself Dynamics. You can look it up. We have a recent paper in BAMS. But of course, there's a number of groups who have done this, and of course, you can do really spectacular quantitative lab studies. And this is all because if you start spinning a fluid, it starts behaving in funny ways. And here's an image from a satellite of Earth. You can see these 2 beautiful tropical cyclones, which of course, wouldn't exist without rotation. I won't talk much about tropical cyclones, but this is just a nice image. So, a fundamental way of looking at this is to look at the Rossby number. So the Rossby number is defined as the ratio of inertial to Coriolis forces. So it's defined here as U, a characteristic wind velocity, over F, the Coriolis parameter, and a length scale L. And that's really just approximately, some wind speed over the rotation rate of the planet. And so as the rotation rate of the planet changes, so goes rho, RO, Rossby number. And then as a result of this, a number of people have noted, of course, there's this huge range of climates that results simply from the variation rotation period of different planets. So this is a little figure from Showman et al. From 2014, in which you can see the rotation rate is the x-axis, and what's plotted on the y-axis is the latitude of the transition between a tropical region and the so-called extratropics. And I'll divide the rest of this bit about circulation into discussion of extratropics and tropics. And this is obviously schematic, but the point is that around one rotation day, a rotation period of 1 day, so this is the Earth case, there is basically a nice division between a tropical region bounded around 30 degrees around the equator and an extratropical region. if you increase rotation rate, then the extratropics become smaller and smaller at the tropics become larger and larger at the expense of the extratropics. And at some point, you get to a situation where really the tropics are from obviously a dynamical sense. The tropics really take up the entire globe. So starting with the extratropics. The extratropics of quickly rotating planets sustain strong temperature gradients and therefore sustain baroclinic instabilities. And by baroclinic instabilities, I mean essentially wave motions that have a vertical structure, and this is all due to the fact that there's a horizontal temperature gradient across these. And this can be evaluated with this thing called the Rossby deformation radius (LD), which is, I mean, it's defined here as n is essentially a static stability quantification, h is the depth of these, a scale height or so, and again, f, the Coriolis parameter, shows up here. And so what I'm showing you, first of all, actually, let's take a look at this image of Earth. You can see this beautiful winter storm. I think this is on the east coast of the U.S., but this is a spectacular winter storm that you see a very large extratropical cyclone. The size of this is really given, the size of features like this is given by the Rossby deformation radius. And you can see this much more explicitly in the simulation results on the right. These are images from Caspian Showman, where they've taken an Earth-like GCM and simply changed the rotation rate. And so you can see here's the Earth case with omega being the Earth rotation rate. If you slow down the rotation rate, then these features, these wave-like features, which are the baroclinic eddies, become much larger. And as you increase the rotation, then they become a lot smaller. And something else to note, obviously, is that as these features become smaller in length scale, the temperature gradient between the equator and the polar regions increases. And that's a result of the size of these features and the fact that they are therefore less effective in transporting heat from equator to pole. So this is obviously very important part of the energy budget of the Earth. Here are some examples from simulations, again, Earth-like simulations from this recent paper, Wang et al., which I think is still in press. Again, showing you a range of rotation rates from 1/2 to 4. So this is equivalent to what I was just showing. And in this case, I'm showing you, I should probably have mentioned the previous one was surface temperature. Here we have wind speeds somewhere in the atmosphere. You can see very clearly that there are these jet features that form at the extratropical latitudes. And as you increase the rotation rate, as the rotation rate increases, the number of jets that fit into the planet also increases. And this is obviously due to just the rotation rate. In the case of the slowest rotation rate here, half of Earth's rotation rate, you have this very regular pattern of sort of a wave number 4 baroclinic wave that is identified in this paper as a regular pattern. As you increase the rotation rate, the pattern becomes less regular, and you have a mixed number of waves. Okay, and the other important point again is to show that there are, in this case, maybe 3 different jets, potentially 4, depending how you count them. All of which fit into the extratropics just simply because the rotation rate is much faster and because the Rossby deformation radius is much lower. In the extratropics, Rossby waves in general, accelerate these jets. And so here I'm showing again the omega equals 2 case, so twice as fast as the Earth. You can see there's 2 jets, potentially a subtropical jet. That's another story. But here's a schematic showing you how these eddies accelerate the jet. So you have the jet region shown here by these wavy lines. And so this is an eastward jet in which baroclinic instabilities generate Rossby waves. And these Rossby waves then propagate in latitude. But because of waves, individual air parcels oscillate back and forth. But through the dynamics, these parcels are oscillating in these sort of slanted paths. And so what ends up happening is that to the north of these of the jet region, parcels that are oscillating back and forth oscillate both southward and eastward. And then the other part of the phase is parcels oscillating northward and westward. And so you can imagine a parcel that comes into the jet region is also carrying eastward momentum, and a parcel coming out of the jet region is carrying away westward momentum. And so that is a net loss of westward momentum or a net gain of eastward momentum into the jet, and of course that is exactly the mechanism by which these jets get accelerated. So this is how you get eddy-driven jets, and of course these are incredibly important for the giant planets. We don't really see planets in our solar system that have terrestrial planets in our solar system that have multiple eddy-driven jets, but the giant planets certainly do. Okay, and so strong temperature gradients and latitude. So here's an image of Earth from reanalysis. Here are the temperature, the annual mean temperature profile with latitude. These strong temperature gradients in the horizontal direction coincide with regions of very strong vertical shear of the winds, and that's obviously how one gets these jet regions, the jet streams of the Earth. You'll note that, especially in the south, there are sort of two jet cores. And so what I've been talking about are the eddy-driven jet, which is essentially the latitude, the poleward core of this jet. There's also the subtropical jet, which I'll discuss in a second. Okay, so now if we go to the tropics, we're talking about low Rossby number regions. The Coriolis parameter depends on latitude. So as you get closer to the equator, that goes to 0, and so all planets have a tropical region, although, dynamically speaking, although it can be very small. So in these panels, I'm showing you results for, again, Earth-like simulations with much slower rotation rates than the Earth, well, compared to the Earth case here. And you can see that there's this region, so in the colors here are stream functions. Again, this is just annual mean. So you can see this Hadley circulation where blue is a clockwise circulation and red is a counterclockwise circulation. And then you have the equivalent of Ferrel cells in the Earth case. As you decrease the rotation rate, these Hadley cells become much, much larger and essentially become global by the time you have a rotation rate that's 16 times less than the Earth. And in the colors on the right panels, you can see the temperature gradients. The temperatures. You can see that the temperature gradients decrease dramatically. The horizontal temperature gradients decrease dramatically as you decrease the rotation rate. And again, so these circulations really act to, these Hadley circulations, the low Rossby number tropics, act to homogenize temperatures very effectively. And of course, Titan is a beautiful example of a low Rossby number planet in general, which has essentially a global Hadley cell. And Titan's surface and tropospheric equator to pole temperature gradients really reflect this. So here's an image of some simulations compared to observations. So just look at the black dots. These are the observations of surface temperature. And you can see that there is some amount of temperature gradient from equator to pole. But really, I mean, if you look at the y-axis, we're talking 2 or 3 degrees Kelvin. That's very, very small. And if you look at the, again, the troposphere, this is from simulations now. The troposphere in this case, is this bottom bit. There's essentially no horizontal temperature contrast, especially near the surface. So this is a hallmark of a global Hadley cell. Now, slowly rotating planets also, but this again, any rotation will have a tropical region, but slowly rotating planets have a tropical quote unquote region that extends to the polar latitudes. And so because of the circulation, there is a transport of angular momentum poleward that results in high latitude, or in the case of higher rotation rates, mid-latitude, subtropical jets. And so that's the other type of jet. And in the case of these slowly rotating planets, you also get super rotating atmospheres. So I'll talk about that in a second a little bit more. But what ends up happening is this Hadley circulation takes air from low latitudes with an angular momentum set essentially by the surface due to friction. That air rises and moves poleward, and that angular momentum is conserved, and so spins up a jet as the air moves closer to the rotation axis, and this is how you end up with these very fast subtropical jets in these simulations. And you'll notice here, I don't know if you can see these numbers, but actually none of these numbers, or very few of these numbers, only at the poles, but at the low latitudes, these numbers are not negative. And so the point here is that all of these winds, across the globe in these simulations, which are of slow rotators, are eastward, meaning the entire atmosphere is moving with respect to the surface toward the east, which means that there is more angular momentum in the atmosphere than the equivalent at the surface. And so these are super rotating atmospheres. So again, with sufficiently low Rossby numbers, Venus's and Titan's atmospheres are both very strongly superrotating. So these are observations of the Venus atmosphere, a number of different observations. You can see very clearly that there's just this dramatic increase in the wind velocity with altitude, and this is, some of these are near the equator, and so this is again the hallmark of superrotation. You have very fast positive winds. Positive meaning eastward, or in the case of Venus, westward, because Venus is flipped. On Titan, the same story is true. This curve here shows the Huygens probe measurements. Again, you can see very strong increase in the zonal winds at low latitudes. Again, a hallmark of superrotation. There is this dip here, which is surprising and is sort of a different story. I may mention it later again. But so this set of observations, these two planets sort of confirm our understanding of these low Rossby planets. So the instability or an instability that leads to superrotation in these slow rotating planets, at least in simulations, is this coupled mode of Rossby waves and Kelvin waves, the equatorial Kelvin waves. The details are not all that important, but the point is that there is this mode which is barotropic, meaning there is not a vertical structure dependence, which is strongly dependent on the Rossby number. So here I'm showing you the growth rate of this mode. This mode is this is an illustration from this paper, Wang and Mitchell. The growth rate of this mode as a function of Rossby number, also with the Froude number, but you can see that the dependence of Froude number is much weaker. It's not, the details there again are not all that important. But you can see a very strong dependence with Rossby number. So as Rossby number goes up, again, that means that the rotation rate is going down. You see the growth rates really peak up here. And if we plot the solar system planets on here, or simulations that reproduce solar system planets, you get, from a cold start, meaning a simulation with zero winds, you start moving across these dashed lines. This is where Earth sits. This is where Mars sits. Obviously below the region where this instability grows. But if you get to slightly higher rotation rates, and to the Titan case in particular, you move through this zone. And so this instability becomes active as you move through these. And so again, Titan is exactly where we would expect it to be in terms of this instability that leads to superrotation. And what's happening is that the coupling of these two waves converges momentum into the equator, up gradient. And so this is a fundamentally different mechanism than the eddy-driven jets that I was describing earlier. Okay, so what we have here is a picture with Hadley cells at low latitudes, or in the case of slowly rotating bodies, all latitudes, where there's rising motion at low latitudes. And then as a result of that, energy divergence and energy transport towards the high latitudes. And of course, this is acting in response to the differential heating due to insulation. At the same time, these Hadley circulations transport momentum, which then drives the subtropical jet. Now, if we add the extratropics here, notice the different latitudes here. You have the low latitude tropical regions, the subtropical jet, and then these baroclinic eddies, which are very difficult to draw schematically, so bear with me. And diffusive energy transport, again, poleward, but also momentum transport into the jet regions. And so you have these eddy-driven jets. And I've drawn these right next to each other. Looks like two eyeballs, but I've drawn them next to each other just to illustrate that on Earth and actually on Mars as well, I think. The subtropical jet and eddy-driven jet merge, essentially. There's a single jet. When you speed up the rotation rate, then they start to separate. Okay, so now I'm going to move to hydrologic cycles. And I'm going to go the other way and talk about the tropical circulation first, and the impact of hydrologic cycle there, and then to the extratropics. So here, the Hadley circulation converges moisture towards the region of upwelling. So I was just showing you in these schematics, the region of upwelling is here. There's a return flow near the surface, and of course, because of the structure of the atmosphere, the temperature profile of the atmosphere, the lower atmosphere can hold much more water than the upper atmosphere. And so the return flow converges moisture into this region. And so this is how one gets the intertropical convergence zone on the Earth. This is an image of evaporation minus precipitation from reanalysis. So there's a convergence of moisture near the surface at these low latitudes, and of course that leads to then explosive moist convection, and that's the ITCZ. A similar thing happens on Titan. So this is just a snapshot of clouds on Titan observed by the Cassini orbiter. You can see very clearly this beautiful band of cloudiness. It's maybe a little deceptive because it doesn't. Titan doesn't behave quite in the same way. It's much more bursty. But the point is that you have a similar behavior on Titan. And of course, you expect the Titan case to be like this globally, since its rotation is slower. So this is what I was describing earlier. There's a convergence of moisture as a result of this circulation. So the return flow near the surface carries moisture into the low latitude regions. In the extratropics now, there are these storm tracks, which are again related to the baroclinic eddies I was talking about earlier. So here on the left is eddy kinetic energy in the colors. Never mind the black contours, which show the location of storm tracks, and this is really where these baroclinic systems travel along. So they really travel along the two ocean basins. It's a little bit simpler in the south because there's no continents to get in the way. And here's a schematic that shows how these things couple sort of to the background circulation. So in the gray arrow, you can see the jet stream. There's waviness, and that's due to the baroclinic instability. All of this is manifested on the surface in terms of high pressure systems and low pressure systems, which carry moisture. And then in these dashed white arrows, you can see the transport of eddies. And again, you can see that the eddy activity in the annual mean, in the longitudinal mean, which is depicted here on this right wall, moves up and poleward. And it's this poleward movement of the eddies that again transports the momentum away, the westward momentum away from the jet, accelerating the jet. So this is what I was describing earlier. What's interesting is actually even slowly rotating planets like Titan may have shallow extratropical zones. So now I'm getting a little bit more into the subtleties here. But we have simulations of Titan where in the boundary layer, there are very clear baroclinic structures. So this is specific humidity in the boundary layer of Titan from simulations that I've run. You can see there's very clear signature of baroclinic structure, meaning that there's a variation with height. And then if you take an annual average of the stream function, you have very clearly the Hadley circulation I was describing, again, in the boundary layer. Above it's a little more complicated, but in the boundary layer you have this Hadley circulation. But actually at high latitudes, you have these very shallow Ferrel cells, which result in the averaging over eddies like these. And so actually it turns out that even though I was just telling you that slowly rotating planets have these global Hadley circulations, it seems like even Titan, with a rotation rate that's 16 times slower than Earth's, there are still extratropical zones. I think probably once you get to a rotation rate like that of Venus, then something like this completely goes away. That's just based on intuition and what I've been talking about. Okay, on Earth, the majority of extratropical transport of moisture occurs in these atmospheric rivers, which are related to these systems that I was just describing. So these are low pressure system. You get a cyclone. If you remember that image of an extratropical cyclone, the winter storm that I showed you earlier, it's a related thing. But you get these plumes of moisture coming off of the equator, where moisture is being converged by the Hadley circulation. These plumes then extend into the extratropics. They're drawn out by these systems. So atmospheric rivers are this hot topic in Earth climates. In Earth atmospheric science now, which I think probably can be extended to planetary systems now. But it's not quite as simple. The direction of transport is not quite as obvious. So in the Hadley case, it's the direction of transport is determined really by how the circulation is moving. The direction of moisture transport by baroclinic eddies actually depends on the surface and the boundary layer moisture distribution. So on Earth, of course, we have basically oceans. You can see here, these are different curves of moisture transport at different time scales. But basically, in all cases, you have positive numbers meaning northward transport in the northern hemisphere, negative numbers meaning southward transport in the southern hemisphere. And that's obviously polar transport in both cases. On Titan, though, baroclinic eddies act in the opposite direction, and that's because most of the moisture on the surface and the boundary layer is at high latitudes. And so one comes up with this ridiculous picture here of Hadley circulations converging moisture into the ITCZ, baroclinic systems in which the direction of this arrow actually depends on what's going on near the surface. And cloudiness here, and of course there are these subtropical dry zones. There's obviously, as I've just described, there's a need for understanding what the surface is doing and the very near very near surface atmosphere in terms of hydrology. And so, of course, for Earth, we have atmosphere-ocean models, coupled atmosphere-ocean models. We've heard a little bit about applications of these to other planets, in particular exoplanets. For solar system planets, it's probably more needed. What's probably more needed is to have coupled atmosphere hydrology models. So I'm here. This is just a schematic of something that I've been working on, coupling a hydrology model globally to the atmosphere to really understand the self-consistent coupling between these two parts of the hydrologic cycle. And then finally, I just wanted to throw up this and say, what about atmospheric variability? I think this is something that the planetary science community probably should start thinking about more seriously. This is the QBO, the quasi-biennial oscillation on Earth. You can see equatorial zonal winds with the seasonal cycle taken out. You can see there's this beautiful variation that has nothing to do with the seasonal cycle. And this is a wave-driven effect. We know that there are similar oscillations on the giant planets. What about other planets like Titan, like Mars? I don't know very much about this. Maybe this is explored in the Mars community a little more, but I think that there's some exciting avenues for future development. And then finally, the solar system paleoclimates offer another avenue for exploring planetary climate diversity. We've already heard a little bit about this. Earth has a hugely rich history of paleoclimate diversity in which there are all sorts of climate states to explore, and which we can interrogate with data through the geologic record. It seems that Mars has similar systems. We've heard a little bit about this, and I'm not going to step into that discussion. And then Titan also seems to have this. So this is a map of Titan showing empty lake basins in the South Polar region, which obviously suggests that at some point these lakes, these basins were filled with liquid, and so that probably tells us something about the past climate of Titan. So there's a lot to explore here. So I'm going to end with just some outstanding questions. I'm going to skip these because I found them less interesting. But as I mentioned, atmospheric rivers are a hot topic in Earth climate science these days. I think we should really start exploring these in the context of planetary climate. So do atmospheric rivers or similar phenomena occur on planets other than Earth? This is probably an interesting question to explore in terms of comparative climatology. Another important question is what maintains the atmospheric superrotation of Venus to Titan. I told you of a mechanism that starts to develop it. In simulations, this is the mechanism that initiates superrotation, but actually it's probably a mechanism that shuts down after the superrotation is developed. And so this is still an outstanding question. What maintains the atmospheric superrotation of slowly rotating planets in our solar system? And then, of course, what are the impacts of seasons? Again, there are some folks who have been discussing this at this meeting, Scott and others. Eli had posters on this. So, this is something we've started to think about, but it's important, and I really didn't go into it. And of course, a related question is, what does climate variability and atmospheric variability look like across the solar system? I hinted at this with the QBO, but there's probably a lot to explore here. And of course, how does climate variability depend on planetary properties like rotation rate or other things? And finally, there are a number of other things to explore. What's the role of topography, other non-axisymmetric forcing like localized convection, and then questions like that relate to paleoclimate, like what are the mechanisms that control glacial and interglacial cycles on Earth, and are these relevant to comparative planetology of the solar system? So I'll leave these up and hopefully take questions. Thank you.
So we can take one and maybe two quick questions.
Could you comment on the role of gravity waves, which are obviously very important for stratospheric circulation in Earth, and how they may play a role in other planets?
Thank you for that question. So the QBO is driven by gravity waves. So that's the wave driving that sets the quasi-biennial oscillation on the Earth. Actually, it seems like that dip in the zonal wind of Titan may also be caused by gravity waves coming up from the troposphere. That's a really interesting question because what produces those gravity waves is a completely open question. Presumably it's convection, but again, convection is very sporadic, and yet that dip in the zonal wind seems to be permanent. So, it's a great question. Let's explore that a little more. Yeah.
Quick question.
So you sort of intimated that the equator to pole temperature gradient on Titan was really small, but isn't it actually really big? I mean, Titan is a smaller body, so the air parcels don't have to move so far. It's slowly rotating, and the column mass is very high. So why isn't the equator to pole temperature gradient, a tenth of a Kelvin, not 2 or 3?
Yeah, that's another good question. I wouldn't say that it's really big, but it is perhaps surprisingly big. And I think part of the reason is the surface is an important component there. The surface has a low heat capacity on Titan, as you know, and therefore it's more amenable to seasonal changes. And on top of that, evaporation from these polar liquids probably cools the polar surface relative to the equator. And so that in fact drives the temperature contrasts that probably feed these baroclinic eddies that I was describing on Titan. And so these are surprising features, honestly. Again, these are very shallow, but you're right that the surface of Titan is a little more complicated than I made it out to be at the beginning.